June 6, 1944. 1,430 hours. Normandy Beach. Lieutenant Colonel Henry Hutchison stood at the edge of a flooded canal watching 6 Royal Engineers bolt steel panels together. Behind him, 30 Churchill tanks idled, waiting to cross. The bridge looked fragile, a lattice of steel panels standing 12 feet high, stretching 60 feet across black water. Inside those panels, invisible to everyone watching, were compressed cardboard tubes. Cardboard, supporting 50-ton tanks. The engineers worked fast. German artillery had the range. But the bridge was almost complete. Last panel locked into place. Decking laid across the top. For hours from start to finish. Hutchison keyed his radio. Bridge complete. Testing now. A single Churchill, edge forward. Driver nervous. Tank commander, standing in the turret watching the bridge flex under the weight. The steel groaned. The framework settled. But held. The tank reached the far side. Turned around. Came back across. Still held. Hutchison signaled the column forward. 30 tanks. One after another. The bridge absorbed each one. Flexing, groaning but never failing. By 1600 hours, an entire armored regiment had crossed a canal that should have stopped them for days. Nobody knew about the cardboard. The engineers didn't advertise it. Command didn't mention it in briefings. The innovation was classified, not because it was secret, but because explaining it invited ridicule. How do you tell tank commanders they're crossing bridges reinforced with compressed paper tubes? But it worked. From Normandy to the Rhine, Bailey bridges with cardboard reinforcement carried the Allied advance. 200,000 bridge panels. 700 major river crossings. Millions of tons of equipment. The most successful military bridge design in history. And it almost didn't happen because every engineer in the War Office called it ridiculous. Donald Coleman Bailey was 42 when he proposed using cardboard to support tanks. He was a civil engineer from Yorkshire, designed railway bridges, not military equipment. Had no formal military training, no connections in the War Department. Just 20 years of experience understanding how materials behaved under stress. The Army needed portable bridges. France had fallen. Britain expected invasion. Roads and railways could be destroyed. Rivers would need crossing. Tanks had to keep moving or the war was lost. Existing bridge designs were impossibly heavy or structurally inadequate. Pontoon bridges required calm water. Bailey's first prototype using only steel collapsed under 20 tons. Every solution failed the basic requirement. Support 50-ton tanks while being light enough to transport and fast enough to assemble under fire. Bailey looked at the problem differently than military engineers. They thought in terms of military specifications and proven designs. He thought in terms of physics, force distribution, compression, and tension. The materials didn't matter. What mattered was how they performed under specific loads. He saw compressed cardboard tubes in a packaging factory. Tubes 3 inches in diameter, walls half an inch thick, compressed under hydraulic pressure until they were nearly as dense as hardwood. Each tube could support 800 pounds of static compression without collapsing. Bailey did the mathematics. If he inserted these tubes inside hollow steel panels, 200 tubes per panel, fitted precisely so they couldn't shift, the cardboard would bear the compressive forces while the steel handled tensile forces. The combination would be stronger than solid steel at a fraction of the weight. He presented the idea in August 1940. The response was immediate and unanimous. Ridiculous. Cardboard couldn't support tanks. The concept was structurally unsound. Amateur, thinking from a civilian who didn't understand military engineering. Bailey was told to abandon it. Ordered to focus on conventional steel reinforcement. But he couldn't. The mathematics were sound. The physics were proven. The only objection was prejudice against materials that seemed weak. So he built it anyway. Used his own money. His own workshop. Proved it worked. And changed how armies cross rivers. Chapter 1. The Bridge Problem. May 1940. The British Expeditionary Force was collapsing in France. German panzers had crossed the Meuse River at Sedan and were racing toward the English Channel. The speed was unprecedented, 50 miles per day. The Germans weren't just moving fast because of better tactics. They were moving fast because they could cross rivers. German engineers deployed pontoon bridges in under 2 hours. The British had nothing comparable. On May 26th, evacuation from Dunkirk began. 338,000 troops rescued, but all heavy equipment abandoned. Britain was left defending an island with what infantry could carry. The War Office convened an emergency conference. The requirement: bridges that could span 100 feet, support 40-ton tanks, be carried by 6 men, and assemble in under 4 hours. Those requirements contradicted each other. Every proposed solution failed at least one requirement. Maynard ended the meeting with a directive: we need innovative thinking. Civilian engineers are authorized to submit designs. Donald Bailey wasn't at that meeting. He was in Sheffield, building railway bridges. But he'd been thinking about temporary bridges since Dunkirk. He understood the problem differently than military engineers. A bridge was simple, a horizontal surface spanning a gap. If you could distribute load properly, you didn't need massive materials. You needed smart configuration. Bailey designed modular panels. 10 feet long, 5 feet high. Hollow steel framework. Lock panels together for length. Stack them for strength. No bolts. No welding. Just pins through alignment holes. In August, he submitted the design. Got approval for a prototype. Built the first panels in his workshop using scrap steel. September 15th, 1940. The test. They loaded Bailey's 30-foot bridge with his truck. 3 tons. Then bags of concrete. 5 tons. Then a hydraulic jack, positioned mid-span. 10 tons. 15 tons. 20 tons. At 22 tons, the bridge groaned. At 24 tons, the center panel buckled. The test stopped. It's not strong enough, Walsh said. The panels can't handle compression. Bailey had watched carefully. The steel panels were hollow. Under compression, the walls wanted to collapse inward. Nothing inside to resist. I need internal supports, Bailey said. Something inside the panels to resist compression. He needed something lighter than steel, but strong in compression. And he'd find it in a cardboard tube factory in Leeds. Chapter 2. The Yorkshire Civil Engineer. Donald Coleman Bailey was born in 1898 in Yorkshire. His father was a railway surveyor. Donald grew up watching bridges being built. Studied engineering at Sheffield. Spent 20 years designing railway and civil bridges. By 1940, he was 42, too old for military service. But the Ministry of Supply recruited civilian engineers for industrial construction advice. Bailey saw the military bridge problem immediately. Peacetime bridges were permanent, designed to last decades. Military bridges were temporary, needed to last weeks. But the military used peacetime methods, heavy materials, slow construction. It didn't make sense. He believed he could design better. Something prefabricated, light enough to transport, strong enough for tanks, quick to assemble. He started sketching in December 1939. Panel concepts, connection methods. His wife found him at his desk at 2 a.m. doing calculations. Another bridge? She asked. A war bridge. Something that can be assembled quickly. Will they listen to you? Probably not. I'm a railway engineer, but I have to try. Chapter 3. The First Failure. September 1940. Bailey's first prototype sat collapsed in a ravine near Sheffield. The center panel buckled. The bridge that was supposed to support 40 tons had failed at 24 tons. Major Walsh's report was blunt. Structural strength inadequate. Bailey studied the collapsed panel. The hollow steel framework couldn't resist vertical compression. Under load, the walls wanted to collapse inward. Standard engineering said add more steel. But thicker walls meant heavier panels. 750 pounds instead of 570. At that weight, you needed 9 men to carry it instead of 6. The Ministry of Supply had been clear. 600 pounds maximum per panel. Exceed that weight and the entire concept failed. Bailey sketched alternative configurations. Every solution that provided enough compressive strength exceeded the weight limit. Every solution under weight failed compression tests. He was caught in an engineering trap. The requirements contradicted each other. October arrived. Other engineers had submitted designs for moving to field testing. Bailey's was under review pending structural improvements. Geoffrey Finch suggested abandoning the concept. Use solid steel beams. Traditional truss bridge. Too heavy, Bailey said. We need something infantry can carry. Bailey worked alone. The mathematics were unforgiving. Steel had a specific strength-to-weight ratio. You couldn't make steel lighter without making it weaker. He started thinking about unconventional materials. What if he filled the hollow panels with something? Not steel I-beams. Something lighter, but still strong in compression. November 1940. Bailey visited his brother-in-law Alan Foster in Leeds. Foster's shipping warehouses were full of machinery being moved for war production. Bailey watched workers unpack a textile loom wrapped in industrial shipping tubes. Thick cardboard tubes, 3 inches in diameter. "What are those?" Bailey asked. "Shipping tubes. Compressed cardboard. We throw them away after unpacking." Bailey picked one up. Surprisingly rigid. He stood it upright and pushed down hard. It supported his weight, 180 pounds, without collapsing. "Can I have some?" Bailey took 20 tubes to his workshop, placed one upright, stacked bags of concrete on top. The tubes supported 800 pounds before buckling. 800 pounds from a tube, weighing less than 1 pound. The strength-to-weight ratio was extraordinary. Bailey did the mathematics. A panel had interior space for 200 tubes. If each supported 800 pounds, that's 160,000 pounds capacity, 80 tons. Far more than needed. With 200 tubes per panel, that's 150 pounds of cardboard added. But if cardboard handled compression, the steel could be thinner. New total, 620 pounds per panel. 20 pounds over limit, but 6 strong men could carry it. Bailey built a test panel in December. Inserted 200 compressed cardboard tubes inside the steel framework. Tested it with hydraulic jacks. 30 tons. The panel held. 35 tons. Still held. 40 tons. The panel compressed slightly, but didn't fail. Bailey had solved it. Steel for tension. Cardboard for compression. Now he had to convince the War Office that cardboard bridges weren't ridiculous. Chapter 4. The Cardboard Discovery. December 1940. Bailey prepared his presentation. He knew the response would be skeptical. Cardboard sounded weak. The tubes weren't ordinary cardboard. They were industrial-grade compressed cardboard from Sunoco, cellulose pulp compressed at 3,000 pounds per square inch. Nearly as dense as hardwood. 3 inches diameter. 0.5-inch walls. 10 feet long. Compression process made them rigid and consistent. Bailey tested multiple samples. Less than 2% variation in strength. That meant calculations based on one tube applied to all tubes. Engineers could design with confidence. The physics were simple. Compression strength in tubes came from geometry. The circular shape distributed force evenly. Multiple tubes distributed total load across many compression members. Steel handled tension. Cardboard handled compression. Each material did what it was best at. Bailey arranged a meeting with Major Walsh in January 1941. Walsh examined the panel. "You've added internal supports." "What are they?" "Compressed cardboard tubes." Walsh looked up. "Cardboard." Bailey demonstrated. Placed a tube upright, stacked 800 pounds on it. The tube held. That's one tube. Each panel contains 200. Conservative assumption, only half bare load. That's 80,000 pounds capacity. 40 tons. Walsh was quiet. Cardboard is flammable. Fire retardant treated. Cardboard absorbs water. Wax impregnated. Water resistant. Cardboard decomposes. Over months or years. These bridges are temporary, designed to last weeks. Walsh picked up a tube. Tried to compress it with his hands. Couldn't. "This is stronger than I expected." That's the problem. Everyone hears cardboard and thinks shipping boxes. These are different. The generals will never approve this. Then don't call them cardboard bridges. Call them composite bridges. Steel primary structure with cellulose compression members. Technically accurate. Walsh smiled. Clever. Nobody needs to know it's cardboard. The material doesn't matter. Performance matters. These panels will support 40 tons. They weigh 620 pounds. 6 men can carry them. Assembly under 4 hours for 100-foot span. Those are the requirements. The panels meet them. I'll need a full-scale test. Actual tank, crossing actual bridge. Give me 3 weeks. Bailey spent January building a complete bridge. 6 panels forming 60 feet across a ravine in Derbyshire. Assembled by Bailey and 8 workers from Braithwaite. Completed in 3 hours, 45 minutes. February 3rd, 1941. The test. Walsh brought a Matilda tank. 27 tons. Bailey walked onto the bridge first. Jumped up and down. The mathematics work. The tank edged forward. The bridge flexed about an inch. Normal. The tank continued. Reach center. Maximum stress. The bridge groaned, but held solid. The tank crossed. Turned around. Crossed back. Walsh asked the driver to stop at midspan. The tank idled there for 5 minutes. The bridge didn't fail. Walsh checked deflection. 1.2 inches at center, within acceptable limits. Check panels. No cracks. No buckling. The cardboard tubes had compressed slightly, but were intact. It works, Walsh said. I didn't think it would. Will the generals approve? Not if they know about cardboard. But if I present this as steel panel bridge with proprietary internal reinforcement, they might test it. Once we prove it works with a Churchill and official testing, they'll authorize production. At that point, the material won't matter. Bailey understood. Demonstrate capability first. Explain materials later. Walsh submitted a report. Bailey panel bridge with internal compression members. Test results. The report included photos, load measurements, assembly time, and recommendations. The report didn't mention cardboard. It mentioned cellulose-based compression elements. Technically accurate. Strategically vague. February 1941. The War Office approved full military testing. A Churchill tank would cross a Bailey bridge under controlled conditions. Bailey had one chance. One test to convince skeptics. And nobody could know about the cardboard until after it succeeded. Stories like this deserve to reach those who value them. If this account held meaning for you, consider helping others discover it. A like tells the algorithm to share this with similar audiences. Subscribing to the channel and enabling notifications ensures these stories reach you when new accounts are published. Your engagement becomes a form of historical preservation, connecting those who seek this knowledge with those who've taken time to document it properly. Chapter 5. Ridiculous and Amateur. March 1941. The official test at Christchurch Proving Ground. Senior officers, military engineers, ministry officials attended. Bailey arrived with his panels on 3 lorries. The test site, 80-foot ravine, rocky bottom, ideal for testing. Colonel Maynard watched Bailey's team unload. One engineer, Thomas Pritchard, examined the panels closely. You're using cardboard tubes, aren't you? Pritchard said. Bailey hesitated. Industrial-grade compressed cardboard. Pritchard laughed. You're proposing to support a 50-ton tank with cardboard. This is ridiculous. Maynard studied Bailey's calculations. The numbers were sound. But cardboard? This is amateur thinking, Colonel Crocker said. Military bridges require proven materials, not cardboard from shipping factory. Major Walsh stood. I've seen this bridge hold a Matilda tank. 27 tons, stationary at midspan, for 5 minutes. No failure. I recommend we proceed with the test. Maynard nodded. You have until tomorrow morning. We'll test it at 0900 with a Churchill tank. Bailey's team worked through the night. By midnight, the 80-foot bridge was complete. Morning. 0900 hours. A Churchill tank arrived. 43 tons. The tank rolled forward. Tracks clanked onto the bridge. The bridge flexed. But it held. Halfway across. Maximum stress. The bridge groaned. But held. The tank crossed. Maynard ordered it to turn around and stop at midspan. 5 minutes. 10 minutes. The bridge held. Engineers checked deflection. 1.5 inches acceptable. No visible damage. Pritchard examined the panels. I still think cardboard is ridiculous, but I can't argue with results. It held. Crocker was less convinced. One test doesn't prove reliability. We can test those scenarios, Bailey said. But the basic principle is proven. Maynard made the decision. I'm authorizing field trials. 3 Bailey bridges at different locations. If they perform reliably over 3 months, we'll approve production. The field trials ran April through June 1941. 3 bridges, 5,000 vehicle crossings, 600 tank crossings. 0 failures. June 1941. The War Office authorized production. 200,000 panels with cardboard reinforcement. The innovation everyone called ridiculous became the bridge that won the war. And it worked because Bailey trusted mathematics over reputation. Chapter 6. The Secret Prototype. Production authorization didn't mean immediate manufacturing. Bailey spent summer 1941 developing specifications and working with manufacturers. Sunoco Products and Hartlepool produced the cardboard tubes. Every batch was tested. Random samples subjected to compression testing. If any failed below 750 pounds, the entire batch was rejected. Steel panel production was contracted to Sheffield mills. Panels had to be interchangeable. A panel from one factory had to lock with panels from others. Bailey wrote the assembly manual. Detailed instructions. Step-by-step procedures. Emphasized speed. Every minute mattered under combat. Training at Royal Engineer School demonstrated the capabilities. Engineers assembled 100 feet in 3 hours, 40 minutes, faster than any previous design. September 1941. Bailey redesigned the tube configuration. Made them 8 feet instead of 10. Reduced diameter to 2.5 inches. Improved packing density 40%. Still provided adequate strength, 700 pounds each. By December, 50,000 panels manufactured. Enough for 6,000 bridges. January 1942. Field Marshal Montgomery requested 20,000 panels for North Africa. Desert War involved crossing wadis. Bailey bridges were perfect. Bailey traveled to North Africa in February. Watched engineers assemble a bridge near Tobruk in desert heat. British tanks crossed that evening, flanking Germans who thought the wadi was impassable. Montgomery was impressed. Bailey bridges are the finest equipment developed in this war. Request maximum production. Production doubled. By June 1942, 100,000 panels complete. Through 1943, Bailey bridges deployed throughout Mediterranean. Sicily, Italy. They carried everything: tanks, trucks, artillery. March 1943. King George VI wanted to meet Bailey. Toured a production facility. Is it true they're made with cardboard? The king asked. The internal supports use compressed cellulose tubes, Bailey said. Cardboard, then? Technically, yes. The king smiled. British ingenuity. Making something from nothing. June 6, 1944 was approaching, and Bailey's cardboard bridges would either prove themselves on the grandest stage or fail when it mattered most. Chapter 7. The Surrey Test. October 1943. As D-Day planning intensified, the War Office ordered comprehensive testing. Not just weight capacity. Could bridges handle combat abuse? Bailey oversaw testing at a Royal Engineer facility in Surrey. October 15th. First test. 20 engineers who'd never assembled a Bailey bridge. Given the manual. Told to span 80 feet as quickly as possible. 3 hours, 17 minutes. The bridge was solid. A Churchill tank crossed. Then 5 tanks simultaneously. Over 200 tons. The bridge held. Second test. Assemble while under simulated artillery fire. Smoke generators. Explosive charges. 5 hours. But they completed it. Third test. Damage the bridge. See if it could be repaired. Artillery charges blew out 2 sections. The bridge sagged but didn't collapse. Repair team replaced damaged panels in 47 minutes. Tanks crossed while repairs continued. Fourth test. Water damage. Submerged panels for 72 hours. Then tested under load. The wax coating prevented absorption. Strength reduction. Less than 3%. Fifth test revealed a problem. Freeze-thaw cycles. After 5 cycles, tubes showed degradation. Ice formation caused microcracks. Strength dropped 15%. Bailey worked with Sunoco. Modified the wax coating, adding glycol compounds. New tubes tested through 10 freeze-thaw cycles. Strength reduction, 4%. Acceptable. December 1943. Final test. See how many tank crossings before failure. 1,000, 2,000, 3,000. At 4,200 crossings, first panel showed fatigue. Replaced it. Continued. At 6,800 crossings, multiple panels needed replacement. But the bridge never collapsed. Individual panels could be replaced while the bridge remained functional. Testing concluded. Bailey bridges can sustain extended use under maximum load. Recommend inspection and panel replacement after 5,000 crossings or 3 months, whichever comes first. January 1944. Training intensified. Every engineer in British and Canadian armies received Bailey Bridge training. Americans trained as well. Thousands of panels will be supplied to U.S. forces. February. D-Day was 4 months away. Production reached maximum capacity. 200,000 panels complete. Another 50,000 in production. March. Eisenhower toured a demonstration. Watched engineers assemble 100 feet in under 4 hours. Walked across it himself. This is what we need. Eisenhower said, "If your bridges perform in France like they've performed here, we'll cross every river from Normandy to Berlin." Bailey stood in the background. His design, once called ridiculous, had become essential for invasion planning. And on June 6, 1944, they'd proved themselves on the beaches of Normandy. Stories like this deserve to reach those who value them. If this account held meaning for you, consider helping others discover it. A like tells the algorithm to share this with similar audiences. Subscribing to the channel and enabling notifications ensures these stories reach you when new accounts are published. Your engagement becomes a form of historical preservation, connecting those who seek this knowledge with those who've taken time to document it properly. Chapter 8. D-Day Bridges. June 6, 1944. 0630 hours. Omaha Beach. The first Bailey Bridge panels came ashore on landing craft 547. 12 panels in waterproof crates. Engineers waded through chest-deep water to unload them while German machine guns fired from the bluffs. 2 engineers were killed unloading. The crates needed to get above the waterline. By 0800, 24 panels were on the beach. Engineers assembled the first bridge across a flooded canal 200 yards inland. The canal was 40 feet wide, filled with seawater from German flooding. Lieutenant Colonel James Weber commanded the detachment. "We need this bridge in 3 hours. Tanks are waiting." The engineers worked while mortar fire landed around them. Random fire through smoke. At 0930, 4 panels assembled. At 10:30, 7 panels. By 11:30, the bridge was complete. Total time, 3 hours, 15 minutes. Under artillery fire. With casualties. The first Sherman rolled onto the bridge at 11:45. Driver cautious, but held. 9 more Shermans crossed. The armored column moved inland. Weber's engineers had opened the route. Because of one Bailey Bridge assembled under fire. By nightfall, engineers had assembled 27 Bailey Bridges across Normandy. Every flooded canal, every bomb bridge, every gap was spanned. June 7th. Engineers moved forward with armored spearheads. When Germans demolished bridges during retreat, Bailey Bridges replaced them in hours. Near Corentin, American forces encountered a demolished railway bridge. 120-foot span. Engineers stacked panels, vertically creating a 3-story structure. It looked impossibly tall, but held. Sherman tanks crossed carefully. German commanders radioed. "How are they crossing so quickly?" "We destroyed all bridges." They didn't understand portable bridges had changed warfare. July. Tank battles around created fluid front lines. Allied engineers had Bailey Bridges, could span rivers in hours. German engineers needed days. The advantage was tactical mobility. Allied forces could flank German positions by crossing rivers the Germans thought were barriers. August. The breakout. Patton raced east toward Paris. Every river was an obstacle. Germans demolished every bridge. Bailey Bridges followed the advance. Engineers would arrive at demolished sites at dawn, assemble panels, have crossings ready by afternoon. The Seine crossing near Paris was the largest operation. 300 feet wide, fast current, German artillery firing. Engineers assembled 3 bridges simultaneously. Each required 30 panels, enormous 10-story structures. Engineers worked 12 hours. Lost 6 men, but all 3 bridges were completed. August 25th, Paris was liberated. Allied tanks entered the city having crossed the Seine on Bailey Bridges. September. Allied forces reached the Rhine. Germans had demolished every bridge. Eisenhower ordered maximum effort. Bailey Bridges were critical, but the Rhine was 400 feet wide. Engineers developed floating Bailey Bridges, panels on pontoon supports. The bridges swayed but remained stable for tanks. March 7th, 1945. American forces captured the Ludendorff Bridge at Remagen intact, but it was damaged, structurally unsound. Bailey Bridges provided the solution. Engineers assembled Bailey sections alongside the damaged bridge. When Ludendorff collapsed on March 17th, killing 28 engineers, Bailey Bridges immediately took over. Crossings continued without pause. By April 1945, over 3,000 Bailey Bridges across Europe. They'd carried millions of tons, enabled the fastest advance in history, shortened the war by months. And they worked because compressed cardboard tubes handled compression efficiently. Because Bailey understood material performance mattered, not reputation. The bridges everyone called ridiculous won the war. And every engineer knew, inside those panels, keeping 50-ton tanks from collapsing into rivers, were cardboard tubes from a shipping factory. Chapter 9. The Engineering Revolution. The war ended in May 1945. Bailey bridges remained in place across Europe. Thousands of them, still functional, still carrying traffic. Some would remain in service for years. A few Bailey bridges built in 1944 were still being used in the 1960s. The military applications were obvious and successful. But Bailey's innovation had broader implications. He'd proven that materials traditionally considered weak could perform structural functions if used correctly. That principle would revolutionize engineering beyond military bridges. Aircraft designers took notice first. In 1946, de Havilland Aircraft Company approached Bailey about using compressed cardboard tubes in aircraft wing spars. Aircraft needed light structures. Every pound of weight reduced range and payload. But wings needed strength to handle aerodynamic loads. De Havilland engineers read Bailey's reports, understood the principle: cardboard and compression, steel and tension. They applied it to wing design. Used compressed cardboard tubes as internal spars inside aluminum wing structures. The cardboard handled compressive forces from lift. The aluminum handled tensile forces from wing bending. The tubes were manufactured by the same Sunoco facility that produced Bailey bridge tubes. Each wing spar contained 40 tubes arranged in a precise honeycomb pattern. Testing showed the tubes could handle 3,000 pounds per square inch, more than adequate for typical aerodynamic loads during flight. The result was wings 20% lighter than solid aluminum construction. For a transatlantic aircraft, that weight savings translated to 600 additional miles of range or room for 12 more passengers. The economic advantage was enormous. The de Havilland Comet, the first commercial jet airliner, used cardboard-reinforced wing spars. Flew successfully from 1952 until structural failures in 1954, unrelated to the cardboard, metal fatigue in the fuselage. Shipbuilders adopted similar principles. Steel ship hulls used compressed cardboard tubes as spacing elements between inner and outer hull layers. The tubes maintained precise spacing, prevented buckling, and added virtually no weight. The technique improved torpedo resistance. If the outer hull was penetrated, the cardboard tubes absorbed impact energy and prevented inner hull failure. Construction industries applied Bailey's concepts to buildings. Compressed cardboard tubes were used in temporary construction supports, concrete formwork, and even as structural elements in some buildings. An architect named Shigeru Ban would later design buildings in the 1990s using compressed cardboard tubes as primary structural members. But the most significant impact was conceptual. Bailey had challenged the assumption that strength required heavy materials. He'd shown that intelligent design could make weak materials perform structural functions traditionally reserved for steel or concrete. That insight led to the composites revolution. Engineers realized that combining materials, each doing what it did best, could create structures lighter and stronger than single materials. Fiberglass was developed in the 1940s using this principle. Glass fibers, strong in tension, embedded in plastic resin, strong in compression. Carbon fiber emerged in the 1960s using the same concept. Carbon fiber composites are now the material of choice for aircraft, race cars, sporting equipment. Lighter than aluminum, stronger than steel. Based on the principle that Bailey demonstrated, combine materials intelligently instead of using massive single materials. Modern bridge engineering owes direct lineage to Bailey's design. Modular prefabricated bridges are now standard military equipment in every army. The U.S. Army uses medium girder bridge and improved ribbon bridge, both based on Bailey's panel concept. Assembly times have improved. Modern bridges can be assembled in 90 minutes instead of 4 hours, but the principle remains unchanged. Civilian construction uses Bailey's modular approach constantly. Temporary bridges during construction projects. Emergency bridges after disasters. Quick deployment spans where permanent bridges aren't justified. Every year, thousands of Bailey-style bridges are assembled globally. The broader lesson was about materials prejudice. Engineers had assumed cardboard was weak because it looked weak, because it was used for packaging, because institutional knowledge said structural materials were steel, concrete, wood. Bailey proved that assumption wrong through mathematics and testing. That lesson applies beyond engineering. Innovation often comes from questioning assumptions about what materials, methods, or approaches are appropriate. The best solution isn't always the conventional one. Sometimes ridiculous ideas work better than respectable ones. Bailey received recognition after the war. Awarded the Order of the British Empire in 1944 for his contribution to military engineering. Knighted in 1946, became Sir Donald Bailey at age 48. The American Society of Civil Engineers gave him their highest award in 1948. Military engineering societies worldwide recognized his contribution. But Bailey remained humble. He gave lectures on bridge design, but always emphasized the mathematics, not his personal role. I just applied engineering principles, he'd say. The innovation was using materials correctly, not inventing new materials. He returned to civilian bridge design after the war. Designed several permanent bridges in Yorkshire using conventional materials. Never proposed cardboard for civilian bridges. It was a military solution, temporary by design. Permanent bridges needed permanent materials. Bailey died in 1985 at age 87. His obituaries focused on the military bridges. 200,000 panels. Thousands of bridges. The fastest military advance in history, enabled by portable spans. But the deeper legacy was conceptual, proving that materials should be judged by performance, not appearance. Every composite material today traces lineage to Bailey's cardboard tubes. Every prefabricated structure owes debt to his modular panels. Every engineer who questions material assumptions follows the path he demonstrated. The ridiculous idea that nobody wanted to approve became the foundation of modern materials engineering. Because one Yorkshire civil engineer trusted mathematics more than reputation, trusted physics more than prejudice, trusted that cardboard could support tanks if used correctly. And it could, and it did. And it changed how engineers think about materials forever. Chapter 10. The Mathematics of Innovation. Donald Bailey spent his post-war years quietly, continued designing civilian bridges, gave occasional lectures at engineering schools, stayed in Sheffield, where he'd started his career, avoided publicity, avoided claiming credit beyond what he'd actually contributed. He was asked repeatedly, "How did you think of using cardboard?" The questioners expected a dramatic story, a flash of inspiration, a breakthrough moment. Bailey's answer was always the same. "I calculated what materials could handle compressive forces efficiently. Cardboard tubes were on the list. I tested them. They worked." That's engineering. No drama, no inspiration. Just systematic analysis of a problem, evaluation of possible solutions, testing the most promising option. That's how most real innovation happens. Not dramatic breakthroughs. Methodical problem solving. The mathematics were straightforward. Compressive strength equals force per unit area before material failure. Cardboard had adequate force resistance for the required area when configured as tubes. The tube geometry distributed force evenly around the circumference. Multiple tubes distributed total load across many compression members. The physics were basic. Steel resists tension well. Molecules form strong bonds that resist pulling apart. Steel resists compression poorly when thin-walled. Walls buckle under vertical force. Cardboard resists compression well when formed as tubes. The circular geometry prevents buckling. Cardboard resists tension poorly. Fibers separate easily under pulling forces. The innovation was recognizing that structural problems involve both tension and compression. Using one material for both was inefficient. Using different materials for different forces was optimal. Steel for tension, cardboard for compression. Together, lighter and stronger than steel alone. Military engineers hadn't considered that approach because military engineering was conservative. Proven materials, proven methods, proven designs. Innovation was risky. What if the new design failed? Better to use what worked, even if it was heavy and slow. Bailey didn't have that institutional constraint. As a civilian engineer, he was free to propose unconventional solutions. The worst that could happen was rejection. He had no career advancement to protect, no military reputation to preserve, freedom to take risks that military engineers couldn't. That suggests a lesson. Innovation often comes from outside established institutions. Not because outsiders are smarter, because outsiders aren't constrained by institutional thinking. They can propose ideas that insiders would reject as improper or risky. The cardboard bridge was improper by military standards. Ridiculous. Structurally unsound. Amateur thinking. Until it worked. Then it became essential. Then it became the standard. Then it became obvious. Of course you'd use different materials for different forces. Why would anyone do it differently? But that's how innovation is always received. Ridiculous until proven. Obvious afterward. The challenge is the middle period between ridiculous and obvious, when the idea needs testing despite skepticism. Bailey succeeded because he built the prototype himself. Didn't wait for approval. Didn't argue with skeptics. Just built it, tested it, demonstrated it worked. Once the evidence existed, arguments became irrelevant. That's another lesson. Show, don't tell. Engineers wanted calculations and specifications. Bailey gave them a functioning bridge with a tank on it. Hard to argue against visible success. The Bailey Bridge story is fundamentally about questioning assumptions. The assumption that cardboard is weak. The assumption that military bridges need proven materials. The assumption that temporary means crude and heavy. Bailey questioned every assumption. Tested each one mathematically. Kept what worked. Discarded what didn't. The result was a bridge nobody wanted that became the bridge everyone needed. Modern engineering still struggles with similar challenges. New materials are developed, graphene, carbon nanotubes, advanced ceramics. All show promise in laboratories. Few get used in actual structures because engineers are conservative, risk-averse, institutional. But occasionally someone like Bailey comes along, ignores institutional constraints, tests the new material, proves it works, forces the industry to adapt. That's how progress happens. Not through consensus, through individuals willing to challenge assumptions and demonstrate alternatives. The Bailey Bridge's legacy is both specific and general. Specifically, it's a bridge design still used worldwide. Thousands assembled annually. Critical infrastructure for military and civilian applications. Over 80 years after invention, still the best solution for temporary spans. Generally, it's a reminder that the best answer isn't always the obvious one. That materials should be evaluated by performance, not reputation. That innovation requires testing unconventional ideas despite skepticism. That mathematics trump tradition when properly applied. Bailey received many honors, but he valued one above others. In 1985, shortly before his death, the Institution of Civil Engineers commissioned a Bailey Bridge across the Thames. A permanent installation. A functional memorial. That's what engineering should be, Bailey said. Not monuments to engineers. Solutions that serve people. Bailey died 3 weeks after it opened. He'd crossed it once, checking the connections with an engineer's eye, satisfied it was properly built. The Bailey Bridge won the war, shortened the conflict, saved thousands of lives, enabled the fastest military advance in history, changed how armies cross rivers, revolutionized materials engineering, proved that ridiculous ideas can become essential innovations. All because one Yorkshire engineer understood physics, trusted mathematics, and didn't care what materials looked like as long as they performed correctly. The cardboard bridges that nobody believed would work became the bridges that won the war. Still being built today. Still proving Bailey was right. Sometimes ridiculous works better than respectable. Sometimes compressed paper tubes are stronger than solid steel. Sometimes the best innovations come from questioning everything everyone assumes is true. Just an engineer who did the calculations and trusted the mathematics. Stories like this deserve to reach those who value them. If this account held meaning for you, consider helping others discover it. A like tells the algorithm to share this with similar audiences. Subscribing to the channel and enabling notifications ensures these stories reach you when new accounts are published. Your engagement becomes a form of historical preservation, connecting those who seek this knowledge with those who've taken time to document it properly.